A very good afternoon, everyone. Myself, Prateek Mishra, and I welcome you all to the YouTube platform of IMS GATE Academy. We are conducting fundamental series for strength of material, where the purpose is to discuss all the basics which are actually required to solve the conceptual question or the application based question. We have already seen how the loads act over any member, then due to this load, how stresses and strains are produced over these members. In the previous session, we have discussed about if the members are connected in series and parallel, how their elongation will happen and how their load distribution will happen, right? In the end of that session, we also discussed about if any bar is hanging under its self weight, how much amount of deformation that bar will undergo, and also we discussed that deformation due to the self weight does not depend on the cross sectional area. So it doesn't matter whatever is the cross sectional area for a prismatic member, right? That discussion was for prismatic member where cross sectional area was constant throughout the length. For a prismatic member, the deformation due to the self weight does not depend on the cross sectional area. It depends upon the unit weight of the material, length of the material, and the Young's modulus of the material. So that is how we have discussed about to calculate the total deformation due to the self weight. We will continue today's discussion with the same topic, that is elongation of bar. But today we will going to start with the how to calculate elongation for a tapered bar. First of all, understand what do we mean by tapered bar. Tapered bar is such a bar where the cross sectional area is changing over the length. For this bar which is shown in the figure, the length of this bar is L and its cross sectional area is changing from diameter D1 at the left end to diameter D2 at the right end. And this is a pure cylindrical bar, right, where you will see that the diameter is constantly decreasing. If over such bar you apply an external load P, if over such bar you apply an external load P, then how much deformation will happen to this bar? This is the discussion, right? When we were using the formula for calculating deformation, delta is equals to PL by AE. In this formula, load is constant and cross-sectional area and Young's modulus of the material is also constant. But for this bar, no doubt load is constant. For all the sections, load acting will be P only. But the cross-sectional area is changing at different sections. Different sections will going to have different cross-sectional areas. So for this condition, how to calculate the total deformation of the bar? Whenever such type of situation is there that any parameter is changing, always keep in your mind you need to integrate the entire thing. Consider an element and then integrate the entire thing, right? Now how to do this? In order to calculate the total deformation for this bar, first thing is clear that the load acting at all the sections is P. Second is the Young's modulus of the material is E. E is the Young's modulus of the material. Now how to deal with this? Let me consider one section XX. Let me consider one section XX, and this section XX is at some distance X from the right support, from the right end where the diameter is D1, right? At this distance XX, I'll consider one element of length dx. This is one element of length dx. For this element, this length is dx. And the diameter of this element is capital D suffix x. Dx is the diameter of this element and this dx is the length of the element. So consider an element, of length dx and diameter d suffix x at a distance of x units from d1. So, d1 is from right side, right? So, we need to consider an element of length dx, and for this length dx, the diameter is dx. Now, how to calculate this dx? Okay. Calculation of this dx is very easy if you remember the principle of similar triangles. This dx can be simply calculated as d1 plus change in diameter d2 minus d1, and this change in diameter is happening over length x, right? So, this dx is more than d1. So, we need to add something on d1 to get dx. Now, how much to add? d1 plus this change in diameter is from d2 minus d1, and this is happening over length L. This total change is happening over length L. So, what change will happen over length x? That we can calculate like this. So, d2 minus d1 is the total change in diameter over length L multiplied by x. So, this is the total diameter dx. This is my diameter dx. Right. Now, we have the diameter. So, if we have the diameter, we know the cross-sectional area of the element. Now, we know the cross-sectional area of the element, we know the load over the element, we can easily calculate the deformation of length dx. Right. So, again what you have to do? Calculate deformation, that is d delta over length dx, over length dx, right? So, d delta is equals to load, which is P, length of the member is dx, area of the member is ax into E. Right. So, this is how you calculate the deformation d delta over length dx. Now, I will just substitute the value of ax. So, d delta is equals to P into L divided by pi by 4 into dx square into E, right? And what is the value of dx? This is entire thing is the value of dx. So, d delta is equals to PL divided by pi by 4 into d1 plus d2 minus d1 by L into x, the whole square into E, right? So, if we need to get the total elongation of the bar, we have to simply integrate this expression. So, on integrating this expression, we get the total deformation of the bar. Total deformation of the bar is 4PL upon pi E d1 d2. 4PL upon pi E d1 d2. This is my total elongation of the bar. So this is how you calculate the total deformation of the tapered bar. So whenever any tapered bar will be given to you, the first thing that you need to do is you need to consider an element of length dx. And over this length dx, you need to calculate the deformation d delta. And this d delta has to be integrated from 0 to L to get the total deformation of the bar, which comes out to be 4pl upon pi e d1 d2. So this is your total deformation of the tapered bar. So if any kind of tapered bar is given to you, you have to consider the length dx, and over that length dx, you have to calculate the total deformation. You have to calculate the deformation over that length dx, and then integrating that expression will going to give you the total deformation, right? Okay. So I hope this is clear to you. This is again an important derivation with respect to the tapered bar, because here and there questions are asked from the tapered bar. If in GATE examination, even in for other examination, as the recently examination was ISRO will be conducted. So in that examination also such kind of expressions are important, right? Okay, moving on with this. We have one question here. Question says that a composite bar of circular cross section is shown in the figure. So both of these cross sections are circular cross sections, right? Upper cross section has a diameter of 10 mm and lower cross section has a diameter of 15 mm. For these two assembly, you have one load acting 25 kilonewton at the junction of these two members. Length of the upper member is 1 meter and the length of lower member is 1.5 meter, and there is gap between the lower support and the lower member. This is the gap, and this gap is 1 mm. This gap is 1 mm, right? Now what you have to do, you have to calculate the support reaction that will happen at point A and at point B. You have to calculate the support reaction. You need to calculate RA and RB, right? Understand this question. First, understand this, how the reactions will develop, okay? So there is a gap of 1 mm between this lower member and the support. So this entire assembly has to undergo a total deformation of 1 mm, then only this lower support will going to provide its support reaction. Okay. So the total deformation for this assembly cannot be more than 1 mm because you have a lower support at the bottom of this assembly, right? So first equation might be RA plus RB, RA plus RB, or I'll write like this, summation of vertical force is 0. So you have RA plus RB is equals to 25 kilonewton, is equals to 25,000, and I'll write this in Newton. This is my first equation, right? Second equation will be deformation of this first member. I'll write this. This is my first member and this is my second member. Deformation of first member plus deformation of second member is equal to 1 mm. I think this is not visible. So this is first member and this is second member. So total deformation delta 1 plus delta 2 is equal to 1 mm, right? Now for calculating this individual deformation, we need to know how much amount of load is present in these two members. For that, we need to draw the FBD for these two members. So this is my first member. For this member, I have one support reaction RA acting like this, right? So same RA will be acting downwards in order to keep this in equilibrium. The diameter of this member is 10 mm. and length of this member is 1 meter. Length of this member is 1 meter, right? So the total amount of load that will be acting in this member 1 is Ra. So the deformation that will be happening in this member 1 will be corresponding to this load Ra. So I can write delta 1 is equals to Ra, that is the load, into length, which is 1000 mm, 1 meter, so 1000 mm, divided by area, which is diameter is 10 mm, so pi by 4 into 10 square, right, into E, which is given as 2 into 10 raised to power 5 megapascal. So this will come in mm. This delta will come in mm. This delta will come in mm, right? So this is my delta 1. Now drawing the FBD for the second member, lower member, this is the lower member. For this lower member, the length is 1.5 meter, diameter is 15 mm, diameter is 15 mm, right? Now if you look into this junction where upper and lower members are connected, if you look into this junction where upper and lower members are connected, upper member will be applying a force of Ra over this member, and this lower member will be having the net force of 25 kilonewton minus Ra. So this is your net force that is present in the lower member. So the net force that is present in the lower member is 25 minus Ra. Okay. So this will be 25 minus Ra. This is also Rb. So Rb is nothing but 25 minus Ra. Rb is nothing but 25 minus Ra, right? So this is my member number 2. So if you write the deformation for this second member, so delta 2 is equals to 25 kilonewton. So this is 25 minus Ra, and both of them are in kilonewton, right? Both of them are in kilonewton. So I'll convert this into Newton, or here also I have to convert this into Newton, right? So I'll write 10 raised to power 3. So this is now in Newton. So I'll write 25 minus Ra into 10 raised to power 3 into length of the member, which is 1500 mm. 1.5 meter or 1500 mm, one of the same thing, divided by area of the member, which is pi by 4 into 15 square, and E is 2 into 10 raised to power 5, right? So this is delta 2, this is delta 1. When you just add delta 1 plus delta 2 is equals to 1 mm, when you add delta 1 plus delta 2 is equals to 1 mm, from there you can get the value of R1 or Ra, and from Ra you can get the value of Rb. So just add these two things. So you have Ra into 1000 divided by pi by 4 into 10 square into 2 into 10 raised to power 5 plus next will be 25 minus Ra into 1000 divided by pi by 4 into 15 the whole square into 2 into 10 raised to power 5. That is the value of Young's modulus, right? So from here you can get the value of Ra. Just do the quick calculation and tell me what will be the value of Ra. So from here you will get the value of RA in Newton. So RA is 19433 19433.96 Newton, right? So when converted into kilonewton, RA comes out to be 19.43 kilonewton. So you have this RA, now calculate RB. RB is 25 minus 19.43. Just do the quick calculation and tell me the value of RB. RB is 5.57 kilonewton. So this is how you calculate the value of RA and RB. So this is how you calculate the value of RA and RB. Any doubt in this? I think this is clear to you. Any doubt in this? I think this is very much clear to you, right? Okay. Chalo, moving on to the next part of the session. And next part of the session, we will going to discuss about an important topic which is termed as stress tensor. Okay. So we have seen different types of quantity. First one is the scalar quantity. Okay. So if I ask what do you mean by scalar quantity, you will say, sir, any quantity which only has the magnitude is defined as the scalar quantity, right? It can be like what I should say, weight of the substance, mass of the substance, not weight, mass of the substance, speed of something, then distance of something. So any quantity which has only magnitude, is defined as a scalar quantity. The examples of scalar quantity are, first one is your speed. Okay, speed only has the magnitude. When I talk about velocity, velocity has magnitude and direction, but speed is a scalar quantity. The next scalar quantity is distance. So anywhere if you roam around, the total length of path covered by you will be the distance covered by you. So distance is again a scalar quantity, right? Then you have mass. Mass is a scalar quantity because mass is actually the amount occupied by any element in the space, and that is defined as mass, right? But if this mass is multiplied by acceleration due to gravity, then it gives us the weight, and weight always acts in the downward direction or towards or along the gravity, right? So weight is some different quantity, but mass is your scalar quantity. Now talking about next quantity, which is the vector quantity. Now talking about the next quantity, which is the vector quantity. So such quantity which has both mass and direction, which has both magnitude and direction are defined as vector quantities. So vector quantities are those quantities which has magnitude, and direction both, magnitude and direction, right? So this is defined as your vector quantity. The example of vector quantity is velocity. Because in velocity, if any element is moving with some velocity, so this velocity will going to tell us the magnitude by which it is moving, and it will also tell us the direction in which it is moving. We represent velocity like this, right? So this vector represents the direction in which the velocity is applied, and this is the magnitude of that velocity. So any quantity which has both magnitude and direction is termed as a vector quantity. The another example of vector quantity is force, right? So if you apply force over anything, if you apply, for example, if you apply force over anything, this force has some magnitude of 25 Newton, and this force also has a direction of I cap. That is, it is acting in the positive x direction. So when any quantity has both magnitude and direction, then that quantity is defined as the vector quantity. Now, this we already studied in the 11th or 12th class. When we come to engineering, we are introduced to one more type of quantity which is known as tensors. Now understand this, what are tensors? So tensor is that quantity which has magnitude and two directions. So tensor is that quantity which has magnitude, and two direction. Direction 1 and direction 2. So a tensor quantity is such quantity which has magnitude and two direction. Now understand this, how we imagine tensor. Okay. So for suppose you have this plane surface. You have this plane surface, right? For this plane surface, this is your x-axis. This is your x-axis. Perpendicular to x-axis, this is your y-axis. This is your y-axis. And third one is your z-axis. Right? Observe this very carefully because this will going to erase any doubt related to tensor. So the primary example of tensor is stress. Stress is a tensor quantity. Stress has one magnitude and two direction. Now understand how it has two direction. For example, if I apply one load, if I apply one load in this direction, if I apply one load in this direction, right? If I apply one load in this direction, this is the load that I have applied. The load applied is F. The load applied is F. Okay. You have applied load in the x direction and the load applied is F. So first of all, this load is acting on this cross-sectional plane, and the direction of any cross-sectional plane is explained by the direction of the normal. So if this is my cross-sectional plane, the direction of normal is along the x-axis. And second scenario is the load which is applied over this section, it is also along x-axis. So for xy, so for this plane, right, for this plane, I name it as plane A. For plane A, direction of normal is along positive x-axis, and also direction of force is along positive x-axis, right? So the direction of plane is also along positive x-axis because it is explained by the direction of normal, and the direction of force is also along x-axis. So if I have to write the direct stress due to this force F, so it is represented as sigma x. This x is the direction of plane, and again I'll write x, which is the direction of force. So this is how I represent any stress tensor. If I represent sigma xx, the first x tells us the direction of plane, and second x tells us the direction of load by means of which the direct stress is coming over this plane. So I'll write this. So if I write sigma xx, so this represents the direction of plane, and this represents direction of force, right? So this is how we write the value of stress tensor. Stress is always represented in the tensor form, or I should say stress is a tensor quantity where it has magnitude, it has two direction. One is the direction of plane over which the stress is coming, and second one is the direction of force by means of which the stress is coming. Okay. So if I just quickly draw this, entire thing. These are the three axes. This is my x-axis, this is my y-axis, and this one is my z-axis. So this is x axis, this is y axis, and this is z axis, right? So if I have to write the direct stress that is coming over, if I have to write the value of direct stress, if I have to write the value of direct stress that will be coming over, just 1 minute. This is sigma xx. This is sigma xx. Why this is sigma xx? Because this is the stress normal to this plane and also due to the force in the x direction. Similarly, if I have to denote this stress, this is sigma yy. Why? Because it is acting on the y plane due to the load acting along the y-axis. So this is sigma yy. If I have to write this stress, so this stress is sigma zz. And why this is sigma zz? Because it is acting on the z plane due to the direct load in the z plane, right? Due to the direct load in the z plane. Now talking about the next type of stress, which is the shear stress. So if I write this stress which is acting in positive y direction. So this stress is termed as tau xy. This stress is termed as tau xy. I'll just take another color. This is termed as tau xy. And how do you know tau xy? So this is the shear stress on the x plane due to the shear force along positive y direction. So tau xy is the shear force on the x plane due to the shear stress on the x plane due to the shear force acting along positive y direction. Similarly, if I draw this shear force, this shear force is acting on y plane due to the shear force acting along positive x direction. So this shear force is named as tau yx. Why tau yx? Because this shear stress is acting in y plane due to the shear force in positive x direction, right? Similarly, if I have to write this shear force, this is my z plane, this is my z plane, right? So if I have to write this shear force, so first of all, this shear force will happen due to the shear force, this shear stress will happen due to the shear force acting in positive y direction, and this shear stress is acting on the z plane. So it is named as tau zy, because it is acting on the z plane and it is happening because of the shear force acting in the positive y direction, right? Similarly, if I have to write this shear stress, right? This shear stress is acting on the y plane, and this shear stress is because of the shear force acting along positive z direction. So I'll just change this color also. This shear force is tau yz. This shear force is tau yz. This shear force is tau yz because it is acting on the y plane due to the shear force acting in the z direction. So this shear stress is equal to this, right? Okay. Now if I write this one, right? If I write this shear stress is acting on the x plane due to the shear force in the positive z direction. So I'll write this as tau xz. This shear force is acting on the x plane due to the shear force in the positive z direction. Next, we have this shear force. We have this shear stress. This shear stress is acting on the z plane due to the shear force in positive x direction. Therefore, this is marked as tau zx, right? So these are the different types of stresses that will be acting over an element. I hope you got that clarity about how to write the stress value for different planes. Here I have shown you the most complicated case where all the varieties of stresses, it can be direct stress or it can be shear stress, that are present, right? So this is how you name all these stress value. Now this stress tensor is represented as, this stress tensor is represented as in the form of matrix. So diagonal elements are your direct stresses, and then you have shear stresses. So on X plane, three stresses will be coming. One will be the direct stress and other two will be the shear stresses. So the other two shear stresses are tau xy and tau xz. Similarly, for Y plane, you have one shear stress tau yx, then you have one direct stress sigma yy, and then you have one shear stress tau yz. Then for Z plane, again two shear stress tau zx, tau zy, and sigma zz. So this is how you write the stress tensor. For this stress tensor, diagonal elements represent the value of normal stress. Diagonal elements represent the value of normal stress. Diagonal elements represents normal stress or direct stress or direct stress, and non-diagonal elements represent the shear stress. Non-diagonal element represent shear stress. Right? This is a symmetric matrix. This is a symmetric matrix. Now, if I am saying this is a symmetric matrix, this can only be a symmetric matrix if these element is equal to this element is equal to this element is equal to this element. So, for this matrix to be symmetrical, tau xy should be equal to tau yx, tau xz should be equal to tau zx, and tau yz should be equal to tau zy, right? Now we will see how these elements will be equal and how this matrix will be symmetrical. So consider this plane over which shear stress is acting, right? This is tau xy which is acting, and this is also tau yx which is acting, right? Consider this plane for which these two stresses are acting, right? Now, if you look into this plane, right, if you look into this plane, or I'll draw one 3D diagram, that will be better. So you have one 3D diagram where this is B, this is H, and this is L, right? This is your tau xy, this is tau xy, and this is your tau yx. This is your tau yx, right? So if you write the total shear force acting over this first plane, so you will write shear force over acting over first plane is tau xy into area of this plane, which is B into H, which is nothing but B into H. This is the total shear force acting over this plane. If I consider second plane, the total shear force acting over this second plane is equal to tau yx into L into B. So this is the total shear force acting over plane 1 and plane 2, right? This is the total shear force. Now, in order to keep this system in equilibrium, it has to have a moment balance, right? So I'll just take the moment about this point O for these two shear forces. Taking the summation of moment about O to be 0. So for shear force 1, I will write shear force 1 into this length. This shear force is acting in this direction and this force is L length away from this point O. So shear force into L length should be equal to shear force 2 into this height H, because this shear force will be acting along this plane, right? So this shear force is this height above this point. So moment due to shear force 2 will be SF2 into H. If you just open up, you will have tau xy B into H. This is the shear force 1 into L is equals to tau yx into L into B into H, right? So if you look into these three terms are common on the either side. So these three terms will going to cancel out and you have tau xy is equals to tau yx. So every time a shear stress will come over the plane, it will be associated with a complementary shear stress. These are known as complementary shear stress. Complementary shear stress. And why complementary shear stress will be there? In order to keep this system in equilibrium. Just imagine only one shear stress is acting, right? So this system will going to rotate about this point O. In order to keep the system in equilibrium, always you will find a complementary shear stress developed in the system. So anytime if you say tau xy, it is understood that tau yx will be there in the system. Okay, so this shear stresses always have a complementary shear stress. Since tau xy is equals to tau yx, same thing you can do for tau xz is equals to tau zx and tau yz is equals to tau zy, right? So this is all about your stress tensor and this is how you represent the stresses. Similarly, if stress is a tensor, then strain will also be a tensor, right? Strain also has a magnitude and two direction. First one, if I say strain, so strain is also a tensor. So strain, tensor. So if I write epsilon xx, this epsilon xx tells me the normal strain in the x direction due to the load in x direction. So this normal strains epsilon xx tell me the strain in x direction due to the normal force in x direction. Similarly, epsilon YY tells me the strain in Y direction due to the force in Y direction. Then epsilon ZZ tells me the normal strain in Z direction due to the load in Z direction. Now we have another representation which is known as gamma XY. This is the shear strain in X direction due to the shear force in Y direction, right? It is also represented as phi XY. Then you have phi Y XY, YZ and phi XZ. So these are the shear strains that will be there. These are the shear forces. One thing I would like to tell you, if you have a stressed element like this, right? And over this stressed element, if shear stress is acting like this, tau xy and tau yx. If this kind of shear stresses are acting over the element, right? So these are the kind of shear stresses that will be acting over the element. This is tau xy again and this is tau yx again, right? So these shear stresses have a tendency to squeeze the member. So this member will going to get squeezed like this. This member will going to get squeezed from the either direction. So if I say this tau xy is the total shear strain due to tau xy and tau yx, right? This tau is this phi xy, which is the shear strain. This shear strain will be due to these two shear stresses, tau xy and tau yx. So shear strain phi xy is due to shear stress tau xy and tau yx. Now understand how this phi xy develops. Half of the phi xy will develop here and another half of phi xy will develop here. When you add these two angles, you will get total value of phi xy. So this angle is phi xy by 2 and this is also phi xy. This angle is also phi xy by 2. So when you add phi xy by 2 and phi xy by 2, you will find that over this xy plane, the total amount of shear stress that will be shear strain that will be coming is phi xy, right? So when we write strain tensor, we write like this. Strain tensor is equals to epsilon xx, then phi xy by 2, then phi xz by 2, then phi, I write xy or yx, it is one of the same thing, phi xy by 2 or phi yx by 2, it is one of the same thing, epsilon yy, then phi yz by 2. Then you have phi zx by 2, phi zy by 2 and you have epsilon zz. So this is your strain tensor, right? And it is very clear that phi xy is equal, phi xy by 2 is equal to phi xy, sorry, yx, phi yx by 2. Similarly, your phi xz by 2 is equals to phi zx by 2 and last phi yz by 2 is equal to phi zy by 2, right? So this is how you simply write the strain tensor for all the elements, and this strain tensor can be used to analyze the gate questions. So if any gate question comes from the strain tensor, I think it is very easy for you to solve this, right? So for today's session, we have understood how to calculate the elongation for a tapered bar. Then we have seen one numerical, and then we have seen how to mention stress and strain as a tensor, and we have also seen the metrics for it. So I hope you have learned a lot of new things. Thank you so much for watching.